Section 4.3 covers the decision that's made at the end of a hypothesis test. If you already have the p-value computed, this is one small step, so this section might go by kind of fast. This is what we know so far from sections 4.1 and 4.2. So the natural question is, what does small mean? If we have a definitive way to determine if the p-value is small or not, then it looks like the conclusion falls right into place. Small effectively is less than the significance level, where a significance level, which is typically denoted by a lowercase Greek letter alpha, it's a threshold for determining whether or not your p-value is small. The p-value is small if it's below that threshold. Typically, alpha is going to be 0.05. You can have other values, and we're going to have 0.1 and 0.01 show up once in a while, but the vast majority of the time, alpha is 0.05, and that's effectively the default value. This is generally the way that it works. What's on this slide is really about all you need to know to get the conclusion right. If the p-value is less than alpha, that's when the results are statistically significant, and that's when you're going to reject the null. If the p-value is not less than alpha, then the results are not statistically significant, and you're not going to reject the null. There is a trap, which goes along with the second option on the previous slide. If your p-value is not less than alpha, you don't want to say that you accept the null hypothesis. That's too strong of a statement. Like it says at the bottom of the screen, a lack of evidence against the null is not the same thing as evidence supporting the null. They're related, and one would effectively be a stronger version of the other, but they're not equivalent. This example is in here to illustrate why you don't accept that the null is true based on sample data. If that's what our null and alternative hypotheses are, so the null is that X is an elephant, the alternative is that X is not an elephant, what we know is that X walks on two legs. Based on that, you'd say, well, we can reject the null because elephants don't walk on two legs. However, what if the piece of information we have is that X has four legs? That by itself is not enough to conclude that X is an elephant, because there are lots of animals with four legs. X might be an elephant, but it might not, so we end up with an inconclusive test here. And generally that's what happens if your p-value isn't low enough to where you can reject the null, if it's not less than alpha. Now we're going to go through the conclusions for some of the examples from the previous section. The FICO credit score example, we ended up with a p-value of 0.37. So if we're using significance level 0.05, 0.37 is certainly bigger than 0.05, so we can't reject the null, and we don't have a statistically significant result. That's really about it for putting a conclusion together. To write out a full formal conclusion is a little bit more work, but that's effectively the idea right there. To add in the context and write out the conclusion a little more formally, we could say something like this. There is not enough evidence in the sample to conclude that the mean FICO credit score has changed. Another Section 4.2 example, the rental cars at Phoenix airports, we had a p-value of 0.014. That is less than 0.05, so we do have a statistically significant result this time, and the null should be rejected. For a full-fledged conclusion with context, now that we're rejecting the null, essentially we can say that there was enough evidence to do so. Like it says toward the bottom of the screen, there is sufficient evidence to conclude that, on average, renting a compact car for a week from Enterprise is cheaper at Sky Harbor, as opposed to the smaller Mesa Airport. Okay, well, what if the significance level had been different? What if alpha had been 0.1, or what if alpha had been 0.01? The p-value was 0.014, less than 0.1, so in that case, you'd still reject the null. If we drop the significance level down to 0.01, 0.014 is bigger than 0.01, then you would fail to reject the null. Although changing the significance level wouldn't have an effect on the art example at the very end of Section 4.2, there the p-value ended up being 0, so it really doesn't matter what alpha is. 0 is going to be less than alpha, whether it's 0.05, 0.1, or 0.01. So for any alpha, you'd end up rejecting the null. As far as the decision process is concerned, effectively what you do is you take something like what's there at the bottom of the screen and shoehorn it into what's toward the top. You start off with a p-value, which is something that has a gradient to it. There is a degree of nuance to the p-value by itself that doesn't exist with the conclusion. The conclusion is just one or the other. One thing then that becomes an issue is you can be wrong. As far as the decision is concerned, there are really four things that could happen. There are two ways to be correct, and there are two ways to be incorrect. If the null is false and you reject it, good. That's a correct decision. If the null is true and you don't reject it, that's also a correct decision. So those are fine. We're not worried about those at the moment. If the null is true but you reject it, so you get a weird sample that has a weird statistic and you end up with a little p-value and reject the null even though it's true, that's an incorrect decision, and that's called a type 1 error. You can also have the reverse, where the null is false, but the statistic ends up giving you a p-value that's too big to reject the null, and so you don't reject the null. That's also an incorrect decision. That would be a type 2 error. Like it says underneath the table, a type 1 error happens when a true null is rejected, and a type 2 error happens when a false null is not rejected. It's really easy to get those backwards. I think the best thing to do is memorize one of them and then just remember that the other one is the reverse. The way that I've personally always done it is that I have the type 1 error memorized, and then I think, okay, the type 2 is the other one, so I just have to flip those two pieces in the sentence around. In the Phoenix rental car example, the p-value was 0.014, and thinking about the original alpha, where we started off with alpha being 0.05, we'd reject the null because the p-value is smaller than alpha. So there would be the potential for a type 1 error when you're rejecting the null, and that would happen if the null is actually true, but you throw it out. In this case, if there's no difference in mean rental car price between the two airports, but we ended up concluding that there was, that on average the Phoenix one was cheaper. In the FICO credit score example, we had a big p-value, 0.37, so we didn't reject the null, and that leaves open the possibility of making a type 2 error, which would happen if, in reality, the mean FICO credit score had changed, but based on the p-value we had, we didn't have enough evidence to throw that null hypothesis out. This is copied over from our book, this idea of an analogy to how a trial works. Essentially, the null hypothesis would be a statement that the defendant is innocent, and the alternative would be that the defendant is guilty. So in a trial, the burden of proof rests with the prosecution, and they have to prove beyond a reasonable doubt that the defendant is guilty. Also with the conclusions, the possibilities are guilty and not guilty, rather than guilty and innocent, kind of like how here the possible conclusions are reject the null and fail to reject the null, not reject the null and accept the null. Accept the null would be the equivalent of a verdict saying that a defendant is innocent. And there are two types of ways that an incorrect verdict can be reached. Either an innocent defendant could be convicted. That would be like having a type 1 error where you reject the null when the null is actually true. Or a not guilty verdict could come back for a guilty defendant, and that would be like a type 2 error where the alternative is true, but you don't have enough evidence to say that the alternative is true. Now we know that there are a couple of possible errors that we can make, so it makes sense to go through what the probabilities of those errors would be. The probability of a type 1 error is easy. It's alpha. There's no computation that you have to do. It matches the significance level exactly. That picture and what's to the immediate right of the picture is supposed to illustrate that. If the null hypothesis is true and alpha is 0.05, then 5% of statistics are going to be in that red tail. So 5% of those statistics are going to give you a p-value less than 0.05, because based on what's there in that picture, if your statistic was -2, then the p-value is going to be the left tail bounded by -2, so it's going to be less than 0.05. Since the left tail that's there in the picture is 0.05. Certainly if you're starting at -2, that's a smaller tail than if you're starting at -1.366. So what you end up with is that 5% of statistics, the ones that are in that red tail, would lead to rejecting the null. The probability of a type 2 error depends on several factors. We're not really going to cover this here, but if you end up doing it in the future, usually the thing that software will compute is not the probability of a type 2 error. Usually it will compute power, and power is 1 minus the probability of a type 2 error. So ideally you'd want the probability of a type 2 error to be low, so you'd want the power to be high. The other thing on this slide is that you do have options for alpha. 0.05 is by far the most common value, but if one error is a lot worse than the other, then that might push you in another direction, maybe toward a smaller alpha or toward a bigger alpha, depending on which error is worse. You're never going to have to pick out an alpha in this class, but there will be scenarios where alpha isn't 0.05, where it can be something else.